Okay, so back to some more notions related to functions. So maybe that supremum infimum business, okay, we'll discuss it later on more examples. We'll get used to all these notions. We're going to discuss them a lot, okay? The point is that your goal, what you want to achieve, is really being able to read these notions intuitively off graphs, off pictures, and simultaneously know the precise definitions. So when I say, for example, an even function, it's good to think of a function that has like a symmetry with respect to the y-axis. That's how you should think of an even function. But if you want to prove that something is an even function and you have the formula, you need to be able to write the definition, to write that f of x equals f of minus x. So it's really bridging an interplay between those two aspects, two viewpoints. The intuition, the math thinking, which is very pictorial, a lot of things going on the way you're used to, and the precise aspect, the rigorous definition of every property and how to work with it. Okay, and that takes time. It takes time to absorb, and we'll do it gradually. Okay, so the next notion I want to discuss is operations. Operations on functions. So just like when we defined supremum, we defined the supremum of a function using the notion of a supremum of a set, we're going to do the same thing here. I want to define what is f plus g. How do I add two functions? A priori, there could be many ways. You could think, for example, take the graph of one, where it ends, stick the graph of the other. Take the graph of one, where it ends, stick the graph of the other. That could be a way of adding functions, right? But that's not how we add functions. So the way we add functions is, what we want to get is a new function. So I have to tell you what is the new function at x. And that's defined as follows. Take the value of the first function at x. Now this is just a number, right? Add to it the value of the second function at x. Okay? So do you agree that there are two plus signs here, but they're very different? I can color this one in pink, but I don't need to. You should be able to see that even though they're both black. This is good old addition of numbers. Do you see that? And this is a new notion. This is addition of functions, defined by adding their values. Clear? So if I ask you what is x squared plus x, at every point, at every x, you have to plug in to x squared, plug into x, and add them up. Okay? And you could start thinking, what would the graph of x squared plus x look like? Okay? Or what would the graph of sine x plus x look like? Okay? Good? And those are very good practice problems. Try that. Try to draw sine x plus x. What you should think, that what you should expect is, if this is x and this is sine, you would expect this sine wave to kind of ride on the x value, and you could expect to get something like this. Can you imagine that? That would be sine x plus x. Good? So that's the definition of addition of functions. Similarly, of course, I can write f minus g, and that would be just subtracting the values. Okay? What is f times g at x? That's just take the value of f at x, multiply it by the value of g at x. And graphing these things is going to get a bit trickier, right? X times x squared is going to be what? It's going to be x cubed. So the picture kind of changes, right? Or x times sine of x. What would that look like? Practice. Do it. It's very, very it teaches you. It's very enlightening. Okay? What is f divided by g at x? F of x divided by g of x. And here we have to remark that what? Right. G of x cannot be 0. That's always the case. Whenever we divide by something, we have to rule out the case of dividing by 0. Good? Okay. And now there's an additional operation, one additional operation, which is something that does not exist in numbers, okay, which is composition. So I'm going to discuss it at a bit more length, composition, because it's something that may be new to some of you. So what is f composed with g? That is denoted by a little circle, and little means smaller than a small o, but bigger than just a dot. It has to be a little empty circle. Okay, so that's the notation. And that's defined by taking x, doing g to it. You get something, right? Whatever you get, do f to it. F of g of x. That's the definition. Okay?
I have one question to the division.
Division, yep.
Functions. I mean, it can happen to every function that g of x is 0. Won't it happen that in that case it's just an asymptote?
Okay, if the function g is 0 at some point, at that point, the quotient is not defined. You cannot define the quotient, you cannot define a quotient of functions at a point where the denominator is 0. Okay? What would happen to the graph? Okay? You can't ask what would happen to the graph at that point. It's not defined at that point. You can ask what would happen to the graph near that point, and that can vary depending on what functions we have. Okay? We'll see examples where, as you say, there is an asymptote, but we'll see examples where not.
Actually, I just wanted to make sure that this doesn't mean that the function is not existing, but that just at this point it's undefined.
Right. It means that it's only defined for x's where g of x is not 0. That's what it means. Okay? But it's not necessarily going to have an asymptote. We'll see examples. Okay? Okay. So back to composition. Let's do an example here, because this is something that may be new to some of you. So let's take, for example, f of x to be sine of x. And let's take g of x, for example, to be 1 over x. Okay? What is... So, by the way, this function is defined for any x which is not 0. Do you agree? Okay. What is, so this is an example, what is f composed with g? Yes? Say that again? Right. So you have to take x, first do g to it. That's what this definition tells you. So when you do g to it, you get 1 over x. To the result, you have to do f, sine. So what you get is sine of 1 over x. Okay? And we're going to discuss this function. It's a very interesting function. I don't want to draw it now. We'll draw it a bit later. What is g composed with f of x? Right. It's something different. It's first do f, sine, then do 1 over what you got. So it's 1 over sine x. And these two are not the same function. For example, where is this function defined? What's its domain? Right, x cannot be 0. Because if x is 0, it's not defined. But for any other x, it is defined. What's the domain of this function? Well, those are excluded from the domain. right? So the domain of this function, the denominator cannot be 0. So all those x's whose sign is 0 have to be excluded. So x cannot be 2 pi k, where k is any integer. So even the domains of these two functions are not the same. Do you see that? Okay, and let alone their graphs, but I don't want to discuss their graphs now. We will do it. These are important functions. Yes? X is not equal to 2 pi k. Integer multiples of 2 pi. Those are the... You're right. I don't need that too. You're right. Pi k. Correct. Thanks. You're right. Yes? Can we do an example of the division? What's sine x divided by x? Right, it's sine x over x. Right, examples of division are just straightforward, right? Just like for all those operations, because you just divide the values. Okay, so I'm not even going to write them, because it's very easy. This is a bit trickier, especially if you see it for the first time. Okay, here we're going to work all the time with compositions. Okay, but good, everybody feeling okay with this? Okay, so those are operations on functions. Okay, now the next notion is going to need a bit of introduction before I actually write down the definition. So I really want to motivate this definition. Why do we need it? So, in fact, let me go back to the definition of a function on this board. And let me remind you a few things. So I'm going to show you a different way of thinking of a function. So remember that a function has a domain and has a range, and it's a rule that sends every element in the domain to a unique element in the range, right? Here's another way of thinking of a function. You draw a potato. Right? It's Hanukkah now. We work a lot with potatoes. So you draw a potato, and this potato we're going to think of as D, the domain. And here's another potato, and we're going to think of this one as the range, E. And we're going to think of F as an arrow that goes from D to E. Do you agree that this is a good way of thinking of a function? Yep. Okay? And the reason I'm introducing it is it's going to be useful for some things. For example, for motivating the two definitions that are going to come now. So, how do I express this business that every x in D should map to a unique element in E? So my way of expressing it is going to be the following. If you take an x here, let me erase this arrow. If you take an x here, let's call it x1, there has to be an arrow coming out of it and mapping it to some guy in E. Do you agree? There it is. So this is F, and it maps it to some element in E. Let's call it y1. Do you agree? Okay. And there should be an arrow coming out of any x here. So if this is x2, there's going to be an arrow coming out of x2. Do you agree? Can the arrow coming out of x2 land also on y1? Is that legitimate? Yes, it could. Okay, so there could be two guys being mapped to the same image. For example, -3 and 3 both get mapped to 9 when f is x squared. Do you see that? -3 squared is 9, and 3 squared is also 9. They both get mapped to the same image. Do you see that? Okay. Another thing that is legitimate is that there could be a very sad y2 here. Do you see that he's sad? Why is he sad? Right, he doesn't have any arrow coming into him. Okay? He was left out. That's not a nice feeling. But that's legitimate in the definition of a function. For example, if you take -2, there's no arrow coming into -2 if that f is x squared. Nothing squared gives you -2. Do you agree? Okay? So these two things that happened here, these two phenomena, are legitimate in the definition of a function. Let me express that by writing here, okay. This is okay. It could happen. There are things that cannot happen. For example, so here's potato D, and here's potato E. They went on a diet so they can fit on the board. Suppose we have x1 here, and suppose we have y1 here in the range and y2 here in the range. It can never happen that the arrow from x1 goes both to y1 and to y2. Why can that never happen? Because it's unique. A unique element f of x to every x in D. This is exactly saying that these are not unique. This x1 got two images. Wrong by the definition of the function. Ami, we would appreciate it if you can turn off the heating. Half the class is falling asleep. Bad idea. I'd rather they were cold.
Can I clear something?
Thank you, Ami.
I need to clear up because we were always taught that the domain is, the D and the ranges are, so now I'm confused with the whole DER. What is
D is the domain, that's where the arrows come out of. E is the range, that's where the arrows go to. This is E, that's where the f of x's live, and D is where the x's live.
then what's the image?
The image is only those guys that are really obtained. Y2 here, Y2 is in the range, but he's not in the image. He's not an image of anybody.
Okay.
Clear?
Yeah.
Okay. So this is not okay. Big no-no. Not okay. Okay? This can never happen in a function. Another thing that can never, this cannot happen because it contradicts this unique word in the definition. Another thing that can never happen is this. A sad x in the domain. Every x, the function has to tell you what to do to it. There cannot be an x with no arrow coming out. Do you agree? The question is, what about a non-continuous function? Completely, this thing is only related to the very definition of a function. It has nothing to do with continuity. Okay? Since we didn't define continuity yet, let's postpone that question till after we define continuity. Okay?
There are points which are not defined.
Let's postpone this. I know you want, but it's wrong. It's wrong. Pedagogic. I can never say that word. It's wrong to discuss things before we actually define them formally. Okay? Because we'll just get lost and we'll lose other people. It's a good question, but try to remember it. Jot it down, and we'll discuss anything related to continuity after we define continuity. Okay? Yes?
So what about the function 1 over x? Because x doesn't have a value.
The question was, what about the function 1 over x? So you're saying, if x is 0, it's not being sent to anybody. But that means that 0 is not in the domain of that function. Okay? For 1 over x, this is not 0. 0 is going to be sitting somewhere out of the potato. Okay? This is D. This is the domain. Okay? Good? So that's this picture here. When graphing, what this means, this is maybe useful to know. So this phenomena here, let me write it. Let's use orange. We didn't use orange yet today. So this phenomena here of an x being sent to two different y's is what would show up on a graph as something like this. Okay? So that snake, that blue snake I drew there, is a curve. It's something that exists. How do I know it exists? I just drew it. But by definition, it cannot be the graph of a function. Not every curve can be the graph of a function. Why? Because there is an x here, that gets 3 different values. Do you see that? 3 different y values for the same x. Do you see that? Therefore, this curve cannot be the graph of a function. This just happened. Okay? Sometimes this is called the vertical line test. If you can draw a line crossing the graph at more than one, draw a vertical line crossing the graph at more than one point, that graph is not a, that curve is not a graph of a function. Clear? Yes.
If x2 was belongs to the domain.
It is here. It's in the domain. It's in the D potato.
But does it have to assign a unique element?
Yes. To every x in the domain. So you can't have an x without an arrow coming out.
So therefore, this is not a function also because x2 didn't assign.
Right. These are 2 phenomena that can never happen in a function. They're not okay. Yes.
Can you show graphically the x2 being like not assigned?
Oh, good question. Can I show graphically x2 being not assigned? So that's a bit tricky, because if it's not assigned, then you would think, okay, then it's not in the domain.
Yeah.
So how do I express graphically the fact that an x is in the domain but does not have a value? I can't using this drawing. That's why I introduced these potatoes. It's really not because of Hanukkah. Okay?
So it's just wrong to plug the x2 into the domain.
No, you don't plug something in the domain. If there's an x to which f does not assign a value, that x is not in the domain.
That's what I'm saying. It's wrong.
Right. These things cannot happen. Okay? So these things can never happen in a function. All the examples that we had, these things will never happen. Okay? These things can happen in the function, but sometimes we don't want them to happen. Because if they happen, some things can go wrong. Okay? So let me show you. So maybe let's write that. Let's write this here. Maybe let's just write the definitions first, and then so there are 2 definitions, and the definitions are going to say what does it mean for a function not to exhibit those 2 okay things. Okay? So f is called 1-to-1, sometimes denoted like this. 1-to-1. That's what I'm defining. What is a 1-to-1 function? In a domain D, if you take 2 different x's, if x1 is different than x2, then their values under f must be different as well. This is saying that 2 different x's cannot be sent to the same image. Okay? This is saying that this phenomenon that we drew here cannot happen. Here we had 2 different x's. Look at this board a second. We had 2 different x's being sent to the same y. Okay? Which is okay by definition of a function, but we want to rule it out for some functions. Two x's being sent to the same y. Okay? So if this happens, the function is not one-to-one. And the name says it, right? Being one-to-one means every person gets his own spouse. Good? Okay. And the other definition, f, a function from D to E, here it's important to emphasize the domain and the range, is called onto, usually a function goes into the range. It's called onto the range, onto and sometimes onto E, if for any y in E there exists an x in D such that f of x equals y. Let's try reading this line in mathematics. For every y in the range, there exists an x in the domain such that f sends that x into y. So no y is left over. No y is sad. No y has no arrow coming into it. Okay? So a function is onto, again, let's look at this board, if what happened here cannot happen. Every y has an x coming into it. Okay? Let me write, just one second, let me write a few examples and then you can ask questions. So examples. Sine x is not one-to-one. Why is it not one-to-one? For example, sine of 0 is the same as sine of pi. Here are two different x's that both get sent to 0. They have the same y. Do you agree? Everybody? Okay. Sine of x is not onto r. There is no value of x whose sine equals 2. So for any x you plug in here, sine of it is never 2. So 2 is not in the image. Do you agree? I can fix these things by fiddling around with the domain and the range. When I give you a function, I'm the one that defines the domain and the range, right? So when we think of sine, if nothing else was said a priori, then we think of the domain as being the entire real line and the range being the entire real line. But here's sine. Can you tell me how to fix it so that it suddenly does become onto and suddenly does become one-to-one? Right. Take the range to be just negative 1-to-1, and what would be the domain?
Negative pi over 2.
Right. If I just think of sine, the same rule, but different domain and range. I'm going to take just this chunk of the graph, just what I bolded here in orange. Okay, just this chunk of sine. Okay, so what is it? I restricted the domain to be only from negative pi over 2 to pi over 2. And I'm restricting the range to be only from negative 1 to 1. Okay? And to emphasize that I'm doing this, I'm going to erase everything else. Can you see this? I'm going to erase this. Gone. And I'm going to erase this as well. Gone. Now, if I were just to draw this on the board, maybe you wouldn't have recognized this as sine x, right? But this is sine x going from, here's the domain, negative pi over 2, and declaring the range to be negative 1, 1. I can do that. And that's the graph. Do you agree? Sine x on this domain, declaring this to be the range, is 1 to 1 and onto. Good? So once again, the properties rely heavily on the domain and the range. They're not just properties of the rule, of the formula. They're properties of the three factors that together make up the definition of a function. Question?
So an even function can never be 1 to 1, either onto?
Very good. An even function can never be 1 to 1. Does everybody understand the question and why it's correct? Good. An even function always satisfies that x and minus x get the same value. So it's never going to be 1 to 1. Everybody good? Okay. So here's another something to think about. You can think of why this is true. Remark. If f is strictly monotone, whether increasing or decreasing, but if it's strictly monotone, then f is 1 to 1. Any strictly monotone function is always 1 to 1. Okay, think about it a second. Decipher the definition of strictly monotone and 1 to 1, and think why this has to be true. And a very good practice would be try to prove this. Try to write out a formal proof. Okay, a formal proof would look something like this. We are given, and write the definition of strictly monotone. We need to show, and write the definition of 1 to 1. And then show why this definition follows from this definition. Okay? It's not a hard thing to show, but it takes time to get used to writing things formally. Okay? Okay. So, those are these two notions, and I'm going to tell you in a minute why they're important to us. Okay? In a minute. So, let me write, okay, I need to erase some stuff. I think by now we can erase this long list of functions and graphs that we were practicing on. Is this function 1 to 1? No, why not? Right. For example, 0.5 and 0.6 both get sent to 0. Right? All the values between 0 and 1 get mapped to 0. It's not 1 to 1. Is it onto?
No.
Okay. If we declare the range to be R, then it's not onto. Because what is its image? Right, Z. If we declare the range to be Z, then it's onto. So this function is not onto R, it is onto Z. Do you agree? Everybody? Again, takes time to get used to the new language. And this function, see it? Oh, can I repeat the definition?
Like the explanation of the definition.
Yeah, the definition means, let's look at this board. The definition means that this thing that happened here, which we declared as sad, can you look at this board a second? The phenomena that we saw here, that there could be a y in the range with no arrow going into it, this is not an onto function. So the integer value function, the floor function that we just erased, if we declare the range to be R, as we usually do by default if there's no other restriction, then it's not onto. The integer value of nothing is 2.5. Right? 2.5 is a real number that no arrow sends anybody to it. If we declare E, the range, to be just the integers, then it is onto. Okay? So this being onto, just like being one-to-one, both of these properties on this board are heavily dependent on D and E, on what you declare as the domain and the range. And that's what I tried to illustrate in this example of sine. Okay? We restricted the domain and the range, and suddenly a function which was not one-to-one and not onto became one-to-one and onto. And we're going to want one-to-one and onto functions because these are the functions that we're going to be able to invert. These are the functions that are going to have inverse functions, and those are very important. Okay? But I think we'll discuss those only after, only in the next lecture. Okay, so let me give you I want to declare a certain list of functions, which I'm going to call elementary functions. Elementary functions. This is not a universal term. Okay, it is. So you may encounter books where this term does not appear, but I want to use this term. It's very useful in my opinion. So elementary functions are going to be functions that start off with certain families of functions. And here are the families. So the first family is the family of functions which are called polynomials. Do you all know what polynomials are? Okay. So polynomials are functions, let me call it p of x rather than f of x to emphasize that it's a polynomial. Functions of the form coefficients times powers of x. an x to the n plus an minus 1 x to the n minus 1 plus dot 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 in descending powers all the way up to a1x plus a0. So example, 8x to the power 4 minus 5x plus 7. This is a polynomial. Okay? There are coefficients. These are called coefficients. They're just numbers. And each one multiples a power of x. Okay? And the highest power, do you know what it's called? Right. This n is the order of p. So this, for example, is a polynomial of order 4. Or usually it's called degree rather than order. I prefer to use the word degree. Is the degree. Order is also okay. Okay, so this is a polynomial of degree 4. Okay? And do you know what this a0 is called? It's just a number, right? But it has a name. A0 is called the free coefficient. That's what it's called. It doesn't have x's. Okay? So you've all met polynomials before and worked with them, right?
Yes.
Okay. The second, so these are polynomials. That's the first family of elementary functions. The second family is related. They're relatives of the first family. These are called rational functions. Do you remember what rational numbers are? How did we define the rational numbers?
Q with the elements of the integers.
Not just elements of the integers.
M over n.
Right, they were quotients of integers. Remember? The rational numbers were quotients of integers. M over n. Remember that? Rational functions are by definition quotients of polynomials. That's the definition. So they're functions of the form f of x equals p of x divided by q of x, where p and q are polynomials. So an example is 1 over x. This is a rational function. It's the quotient of the constant polynomial 1 and the polynomial x. Do you agree? 1 over x squared. These are very useful functions. Do you agree? And of course, 8x to the power 4 minus 5x plus 7 divided by 17x cubed plus pi x. Yes? P and q are polynomials. We should add something.
So 1 over x.
X is a polynomial. X is a polynomial where its degree is 1, a1 is just 1, and a0 is 0. Do you see that? 1 is also a polynomial. It's a polynomial of degree 0. So all these are gone. And a0, its free coefficient, is just 1. Do you agree? Okay. I just have to add something. P and q are polynomials, and right, q of x cannot be 0. Whenever you divide, you have to rule out the denominator being 0. That's not defined. Okay, so these are rational functions. The next family.
Say that x cannot be equal to 0.
Hmm?
So where you need to take in common.
Say that again?
There you need to take that x cannot be 0. Then already take that.
When I write 1 over x, I wish I hadn't erased this. Okay, maybe I'll. When I write 1 over x, it's implicit that x is not 0. Okay? Sometimes these things are so obvious that I'm not going to write them. So for example,
For q to be 0 also.
no, when I write 1 over x, the denominator cannot be 0. So when I write 1 over x, x equals 0 is not in the domain. When I write this as an example for a rational function, it's implicit. It's understood between us, then this and this are not defined at x equals 0. Okay? Okay. Good. The next family, oh fine, I'll erase this. I know how to draw it again. The next family, family number 3, we'll finish in just a couple of minutes. Family number 3 is the exponential functions. So these are functions of the form a to the x, but this time the x sits up here in the exponent rather than down here, as in polynomials. And the restrictions are that a is greater than 0 and a is not equal to 1. These are standard assumptions. Okay? And these functions tend to look like, for example, e to the x. You've met e to the x before, right? We'll discuss it in detail later in the course, but it looks something like this. Okay, this is what exponents look like when the base, when this a here, which happens to be e in this one, is greater than 1. Okay, so they tend to 0 as you go further out to negative numbers, and they tend to infinity very quickly as you go further out into positive numbers. Okay, and there are some standard techniques of working with these functions which you should know. So I assume you know these things from your past studies, and if somebody doesn't, please make sure to fill that gap. Okay, so come and ask, and you need to practice these things. You should feel comfortable with writing things like a to the x plus y equals a to the x times a to the y. Do you all know this? And a to the x to the power y equals a to the xy, and a to the minus x is what? 1. Right. Good. I'm happy that you all know this. Good. So, and more. There are more of these rules. So you should know these things. You should feel comfortable with them. And the last family, let me put the ... here. The last family that I want to mention, there are going to be more a bit later, but the last family that I want to mention now is trig functions. So we've discussed these. Sine x, cosine x, tan x, etc. We've discussed these. And for these, there's a lot of background knowledge I expect you to know as well. So there are all these things sometimes called as trig identities or trig formulas. So I expect you to know, for example, that tan x is sine x over cosine x. That's actually the definition of tan. Okay? And I expect you to know, for example, that sine squared x plus cosine squared x equals 1. Good. And, for example, that sine of 2x, right, it's 2 sine x cosine x, but it's, in particular, it's not the same as 2 sine x, right? It is the same as 2 sine x cosine x. And there's a big ... here. There are many, many of these. I do expect you to know the basic ones, like the 3 I wrote here, to know them by heart without needing any references. And I expect you to know that there exists many more and to be able to find them if you need them. Okay, so I don't expect you to remember all the double angle and all the half angle and all the sum and difference and product formulas there are. Okay, but you should know that there is a formula for sine x plus sine y. And you should know that there is a formula for sine of 1/2 x. And you should know, they're in every book. And when you see a sine of 1/2 x, you should know that one direction the exercise could take is to use the trig formula for that. Okay? Questions? Will you have a formula sheet on your exam? Usually not. Usually not. So that implies that if I want you to use one of those formulas that I said I don't expect you to remember off the top of your head, then I'll provide it. Okay? I'm a fair guy here. I'm not gonna... Okay. So let's stop now but we'll continue with this list. Okay? So let's stop here for now. Okay, so let's have a 10-minute break.